Now, there's a bunch of ways you could solve this, but I think what you'll find is most useful is to actually take tan of both sides. Now, that may seem rather counterintuitive to you. You're like, where did this come from? Well, I'm going to show you in a second why this is a useful thing. But first, let's just write down the line. Tan of all of that stuff on the left-hand side equals tan of pi on 4. Okay, now why am I doing this? Well, I want you to recall that in order to work out what an argument is and its relationship to the original complex number, if you were to say, let's just do something a bit messy over here. If you were to say have some number a plus ib and you wanted to relate that to the modulus, right? What you would do is you would say, oh, well, I have a right angle triangle sort of implied here, right? There's a right angle here right next to the positive real axis. And so if I'm after this angle in here, then what I need to do is say, if this is a plus ib, then this distance here must be a and this distance here must be b. So you can see the best trigonometric ratio that relates these two together is going to be tan, because tan of theta will be b over a. Let me say that again. Tan of theta, right? So tan of your argument that you're after is going to be b over a. So what I can say is that tan of some complex number, right? Or rather tan of theta, which is the argument of a plus ib, that should just be equal to tan of theta, which is b over a, opposite on adjacent. So I'm going to go ahead and write in b over a there. So I'm going to say since tan of arg a plus ib equals b on a, I can actually do some working here because these tans are going to be able to get rid of all of the argument notation that sort of has the y, which I'm after, kind of nestled inside all this messy stuff, okay? So I'm going to use this fact to then say, okay, well, what is tan of the argument of each of these complex numbers, and they will come into play later on. So since tan of arg a plus ib equals b on a, I can say tan of arg of iy minus 1. That's going to be b over a, except what's b and what's a in this situation? Well, b is the imaginary component, which in this case is y. And then what is a? A is the real component of this complex number. So the real component here is -1. So I'm going to have y over -1, which of course I can simplify as -y. So I'm going to, tuck that away. I will refer to that after I've gotten the rest of this line in terms of tan. So I'm going to do tan of the other argument now, which was, if you recall, iy plus 1. So what's that equal to? Well, the imaginary component's the same, so the b is the same, so it's y over. And then in this case, my a is not -1, it's +1. Okay, so therefore I get y. Now, this is good. This enables me to work out what tan of these arguments is. But just watch out here, right? I can't just put tan on each of these as if like I've got a set of brackets that I can just expand. This is actually a compound angle, right? I can say, but tan of a compound angle like a minus b, and that's the situation you've got here, right? Arg of iy minus 1, it's some angle, and I can call that angle capital A. And arg of iy plus 1 is some other angle, and I can call that angle b. So in fact, I might even label that as so, call these a and b. You can go to the reference sheet for this, but maybe you remember this result off the top of your head if you've done this recently in your other course. It's going to be tan a minus tan b. And then it's all divided by 1 plus tan A, tan B. So I'm going to have to use all of this information in order to work with this line here. So let's try and put this in summary, right? I'm going to call this line 1, or equation 1. I'm going to call this one 2. I'm going to call this one 3. And then I'll call this one 4, right? So what I'm going to do is I'm going to take, because I need all of them, right? 2 and 3 and 4, and I'm going to substitute them into 1 because that's the situation I've got. I've got a tan of a minus b, it's going to become this, but then in order to work out what tan a and tan b are, I need my results from 2 and 3, okay? So let's have a go. Substitute those 3 results, 2, 3 and 4, into my main line of working, which is 1. All right, what do we get? On the left-hand side, it's going to be, like I said, this situation. So tan of a minus b, in the first instance, up the top, I'll get tan of a. Thankfully, I've already worked out what that is. It's minus y. So I'll write that up the top. Then the next thing is I've got to do minus tan b. Well, my b in this case is here. So tan of arg iy plus 1, I've also worked out it's just y. So I've got tan a already written like so, and then I'm going to subtract tan b, which is just y. Okay, so far so good. On the left-hand side, I'm still doing the denominator here. I've got 1 plus tan A tan B, which we've just noticed is minus y times y. All right, that's the left-hand side. I've used 2, 3, and 4 in order to do this. And on the right-hand side, I've just got tan of pi on 4, which is a nice exact angle. That is just 1. All right, so we've done a huge amount of work here, right? We have gotten rid of all of the complex stuff out of here, all of the arg notation, all of that, and I have something which I am able to, evaluate just in Cartesian terms. And remember, the reason I'm doing all of this is because I am after, where did it go? Here it is. I'm after some imaginary intercepts, some intercepts on that y direction. So I've let x equal 0, and that's why there are no x's in this equation. Let's start to simplify. So I've got on the numerator minus 2y. On the denominator, I've got 1 minus y squared, and this 1 is just hanging over on the right-hand side. Multiplying through by 1 minus y squared, I've got minus 2y and then 1 minus y squared on the right-hand side. And then, because I know where I'm going, what I'm going to do is I'm going to add y squared to both sides. That leaves 1 on the right-hand side, but at the same time, because I know I'm trying to solve for y, I could go to the quadratic formula, but I'd rather not. I'm sort of set up to do a completing the square thing here, right? So I'm going to take the coefficient of y, I'm going to halve it, which gives me negative 1. I'm going to square that, which gives me positive 1. So that's what I add to both sides. I've now successfully completed the square on the left-hand side, which gives me y minus 1 all squared, and I just get 2 from 1 plus 1 on the right-hand side. Ready to take the square roots of both sides, that gives me plus or minus square root of 2, and now I add 1 to both sides, and I get this result. 1 plus or minus the square root of 2. Now, this is really, really useful to me for 2 reasons. Number one, one of these results, 1 minus root 2 or 1 plus root 2, one of these results is my y-intercept that I'm after. And just having a look at our rough diagram up above here, you can tell which one it is, right? Root 2 is about 1.4. So 1 minus root 2 is 1 minus 1.4. So in other words, it's actually going to be down here, because of course what we're solving represents the whole circle, so that's this negative point down here, which we actually do not want because it's not part of the locus or the graph that we've been generating. I want the other solution, which must clearly be 1 plus root 2. So I'm going to make a statement to that effect. I'm going to say, but on the locus that we generated, y has to be greater than 0. Therefore, y equals 1 plus root 2 only. So this is very handy to me. It means I can go to this, which I've drawn a little more neatly than the other one I had before, and I can say that y-intercept up above, I can simply state this is 1 plus root 2, but do note that this is actually, like, we're thinking about this on the complex plane, so actually it's 1 plus root 2 I, because that's what takes you in the vertical direction. So that's really great. I have a y-intercept, which is fantastic, but I'm not going to abandon that other solution, right? 1 minus root 2 is down here. Now, the reason why this is useful to me is because it gives me this other piece of information which I need to get the Cartesian equation. In order to work out where the center of this circle is, there's a lot of different paths you can go about doing this. I used a bunch of geometric reasoning, deductive reasoning methods in class before, but I actually have everything I need in this line up here. If y equals 1 plus or minus root 2, then there are 2 intercepts on the imaginary axis, and they're both starting from 1, and then you move root 2 up or root 2 down. Now, that's exactly how we define points on the circumference of a circle. You start from a central point, and then you go out a constant distance, which we of course call the radius. So therefore, I can say that 1 plus or minus root 2, in this case, because my circle is centered on the imaginary axis, 1 must be the center, or rather 1 in the imaginary direction, because remember y is an imaginary component, and then plus or minus root 2, that gives me the magnitude of the radius, right? So therefore I can say, if I go root 2 down, this is my point I, because it's y equals 1, so 1i, that's my center, and therefore I can, reason from there, and I did this in class as well, that if I went to any of the other points on the circumference, and I currently only know 2, you can see the distance across each of these, if I've correctly evaluated this, it has to be equal to root 2, because that's the whole idea of a radius. It's a consistent measurement all around. And sure enough, if you have a look at this, this is 1 plus root 2 I, take away I, that distance has to be root 2. Using the fact that this is a right angled triangle and it's also isosceles, you can see that this is going to be also root 2, and by symmetry this is also root 2. So this is all I need now to generate what the Cartesian equation is. I've got the center. It's, in terms of Cartesian coordinates, it's at 0, 1, but in complex coordinates, it's I. So I can say that the circle will be of the form, I don't need brackets there, x squared plus y minus 1 all squared, because you can see I've moved up 1 unit. And then I can say on the right hand side it should be a radius of root 2, so on the right hand side I have r squared, so in this case it's just 2. So that is my Cartesian equation, and you can see I wasn't able to completely avoid geometric reasoning, but in terms of how to find this, this intercept up here, you can still use all of these tools so long as you know a bit of trigonometry and thinking through it. So I hope you found that useful. As I mentioned right at the top of this, I wouldn't recommend this as the first thing that I would go to. I think that geometric reasoning is far more efficient and powerful. Of course, you have to actually include some of that in your working, but I still think it's much less error prone and also far more elegant than having to go through all this algebra in this very, very long and circuitous path.